The third and final video is about logistics. So apparently in big companies, logistics are very concerned with stock coverage. And stock coverage has to do with how much there's a fine balance between ordering too much stock and then you end up having, well, you would have spent way too much money on stock which you never managed to sell. But then conversely, if you order too little stock, then you end up having people who would go elsewhere to find the products that they want. So there's a very fine line between ordering too much and getting too little. And this is where machine learning prediction comes in. What we're going to try to do is see if within our data there are any trends and seasonal patterns which we can use to predict the coming year. And that's exactly what we're going to do in the last stage over here. You have to bear with me over here, this is a bit involved. However, what we're going to do over here is we're loading some product data. In this case, it was the sales for tractor, so number of tractors sold for quite a number of years. I think for the past 3 years or something like that, 10 years, something like that. And first thing we're going to do is, okay, now I have this data. This could have been anything: t-shirts, shoes, gifts, whatever it was, income as well. First thing we're going to do is we're going to say, listen, is there any trends or is the data completely random? If the data is completely random, it's useless trying to predict the future. So we're going to put in two different data characteristic nodes. The first is a periodogram, which shows us if there is any particular periodicity within our data. And there is a very high one at around 12, which is, I guess, pretty obvious considering it's yearly data. Let's have a quick look at the raw data. So if we do something like this, let's put it on a line chart, get rid of that. Okay, so this is our data, right? So it's going for quite a large number of years, and we see this business seems to be doing well because his tractor sales have an upwards data trend, and there is obviously a very obvious seasonal component over here. His sales go up and down depending on the month where we're at. So that would be exactly why our periodogram figured out that there is a periodicity of 12, because it is an annual cycle. It's an annual cycle that repeats. Okay, so we should see something similar in the correllogram. Correllogram is autocorrelation and partial correlation, and yes, in fact, we see the same thing, that there's a high correlation after 12 months, so there's a cycle, and there is also a partial correlation, which means there is something which is not quite explained at around period 7. So there is some periodicity and correlation in our data, which means that this is a good candidate to use for prediction. Now, we can, first of all, extract this seasonal data, this seasonal component of the data, so that we'll be able to explain to our customer, to the logistics of the customer, how their stock should change with time. And if we put this into a season adjustment and say, okay, we have a season period of 12, which means a year, we end up looking at something like this. We have that. Now we see that there's over here a graph which shows us exactly how many tractors we would expect to sell depending on the month, and it's the same period, it's the same pattern repeated after 12 data points. Um, just to give you a reminder, this is how the original data looked. Because of stability issues, a lot of maths, we are actually taking the log of this this data, and here we can see the seasonal component of that data, the trend. So this is the trend, which you can also show to the customer if we want to, and the numbers of tractors sold adjusted for season. But first part of the report would be, listen, we could tell the customer that depending on the month, you can expect to sell more, like this over here, or less, like this over here, a negative number. And that's going to be the first part of our report. So we're going to save that data, which is going to be this here, the seasonal results. Let's open it. And we're saying this is the number of tractors sold, and this is the number of tractors sold adjusted for season. So let's do a very quick calculation here. I'm going to make it equals to okay, that's not a problem. Let's just open a new one. So we're going to say, give me that, minus, don't forget this is log, so we need to actually do 10 to the power of whatever number we have there. Okay. And we copy and paste the same formula for the whole year, which is up till here, December. Okay, so if I now end up putting something like this into our report, we can tell the customer that, listen, you actually need to take the following numbers into consideration when you are ordering. That in January you can expect to sell about 27 tractors less. February similarly. Things start getting better in March, April, you know, you can expect to sell 17 tractors more, and your highest demand peak seems to be in July, where you can expect to sell something like 41 tractors more than usual. So that is where you need to order more or less tractors. Let's get, so that's just one part of the prediction. Now we're going to end up going into actually trying to predict, to forecast data in absolute terms. And what we're going to do over here is I'm just going to take the seasonal adjusted data, because we don't want to, we've already just predicted the seasonal component, so now we've removed that component and we want to work on the seasonal adjusted data. I'm going to split my data into two. We're going to use training data, which is the first from January 2003 going to December 2013, so that's 10 years, and then our testing data is going to be the last 1 year. In other words, we train our algorithm on 10 years and we ask it to predict the next 1 year, and we'll see how well it does. So that's exactly what I'm doing over here. I selected the last 12 months so that we compare our forecast to real data. We're basically training a model over here. Again, I'm not going to go into the math of it, but this ends up giving us a forecast. So if we look at the results, we see that there is a forecast for the number of tractors sold, along with a confidence interval. If we plot this data, so I'm grabbing the forecast and going to put it into a line chart, and obviously compare it to our real testing data, we end up with a plot that looks like this. So our real data is the solid red line, and the dash is the prediction that comes out of the algorithm. The first data point is superfluous. Actually, it's a problem with the interpolation of the graph. But if we look at the others, we actually notice that it did a pretty good job. The first prediction is very close together, and then we see both the prediction and the real data taking a downward turn, and then both the prediction and the real data taking an upward turn where they match almost exactly for a period. Obviously, as we go further into the future, the less certain our algorithm becomes. That is why our confidence interval increases. However, had our customer followed the predictions exactly, he would have only ended up with a significant difference in stock in 1 month over here, which is exactly why we give the confidence intervals, because if he instead follows the sort of higher edge of our confidence, he would never have gone out of stock. And like this, it gives very good guidance towards how much stock a company should order over the next 12 months. This model would need to be revised every so often so that you take into account additional historical data that's coming in. So that would be the very last element that we have that would put into our report. And we end up having a very, I think, informative report for a customer that ends up showing business intelligence with all our rules and exploratory data analysis, fraud analysis, and finally the logistics, which shows a seasonal component as well as absolute forecasts for the coming year. And that concludes our quick tour of data insights.